Hello, and welcome to this clip on acid-base theory. We'll firstly review some of the acid and base theory from your first year before going on to the Bronsted-Lowry theory of acids and bases in terms of hydrogen ion accepting or donation. We'll look at how to distinguish between a weak and a strong acid or base, and the concept of pH, or the idea of pH as a way of quantifying or doing calculations using the large variation of hydrogen ion concentration that we found in acids. And finally, we'll look at the use of the acid dissociation constant to calculate the pH of a weak acid. And it's assumed that you're comfortable with the idea of an acid as a proton donor and a base as a proton acceptor from first year A-level chemistry already. And it's also assumed that you're aware of the common strong acids HCl, H2SO4 and HNO3, hydrochloric, sulfuric and nitric, as well as strong bases being group 1 and group 2 hydroxides. So let's quickly review the acid-base theory you would have done in your first year. So the fundamental idea is that acids are proton donors and bases are proton acceptors. The proton meaning the H plus in each case. So a strong acid dissociates completely, giving the maximum concentration of H+. A strong base also dissociates completely, allowing it to accept a large number of protons per mole in solution. Bases which release OH minus ions into aqueous solution are also called alkalis. So a weak acid only partially dissociates, meaning its dissociation is in reality an equilibrium. So for a weak acid I've given the example of ethanoic acid, CH3COOH, and for a strong base, an alkali, I've given sodium hydroxide as the example. And these ideas just discussed actually marry up with what's called Bronsted-Lowry acid-base theory. So Bronsted-Lowry acids exhibit all these behaviours in terms of being proton donors, and Bronsted-Lowry bases are proton acceptors. So if we look at what H plus does in an acid-base reaction, it's swapped for another positive species during an acid-base reaction. So these are the four main types of acid-base reactions that you'll come across. And there's a reaction, an example of a reaction for each one. What we've got to do to see what the H plus is doing is turn these into ionic equations. So in each case what I've done is I've got rid of what we call the spectator ions. You would have done this last year when you did ionic equations. So eliminating the ions that stay the same either side, you end up with these four ionic equations. It should now be possible to deduce what the H plus is actually doing. It's swapping for another positive species during the acid-base reaction. So the one exception would be ammonia. Ammonia behaves in its acid-base reactions slightly differently, in that the H plus combines with the ammonia directly instead of just swapping for an ion. But in all the other cases, either one or two protons are swapped for another positive species. So this is the role that H plus plays in the reactions of acids. And as you've probably guessed already, this process is called neutralization. And the definition for neutralization is when an acid and a base react to make a salt. So when you're thinking about acids and bases in aqueous solution, you need to think about them in terms of the concentrations of H plus or the concentrations of OH minus. So if OH minus concentration is greater than H plus concentration, the solution is alkaline. If it's the other way around, the solution is acidic. If they're both equal to each other, the solution is neutral. It's worth spending a couple of moments having a chat about weak bases. Weak base can still technically be an alkali if it increases the OH minus concentration. In the example I've given there is ammonia gas dissolving in water. You can see quite clearly that it does increase the OH minus concentration in the aqueous solution. It's just that it's an equilibrium, and the position of the equilibrium will sit well to the left. And it's exactly the same for metal carbonates and metal oxides, two other examples of weak bases that you come across in your first year. So the idea is throughout that we're treating them as things that could possibly produce OH- in aqueous solution. But the important thing to remember is that the equilibrium sits well to the left in all of these ionic equations. So when deciding whether an acid is monobasic, dibasic or tribasic, you need to think about how many protons an acid can potentially release into aqueous solution per mole. So looking at these three examples, HCl is obviously monobasic. If we were to look at sulfuric acid, that's dibasic. And phosphoric acid is obviously tribasic because it's got 3 possible protons it could release. And looking at an organic acid like ethane dioic acid, this example would be dibasic because 2 protons can be released. A conjugate acid-base pair is basically 2 species which can be interconverted between each other by the transfer of a proton. So when we've talked about strong acids, we've mentioned the idea that they completely dissociate. You could actually argue that HCl is in an equilibrium, it's just the position of the equilibrium is very much to the right, as opposed to in the middle or to the left. So in this equilibrium, HCl is the conjugate acid because in the forward reaction it releases a proton to form Cl-. And Cl- is the conjugate base because in the reverse reaction it would accept a proton to reform HCl. So we'd call these acid 1 and base 1 because they're part of the same conjugate acid-base pair. Let's now look at what might happen if HCl is neutralized. So acid 1, which is HCl, loses a proton to become Cl-, which is now base 1. So that's a conjugate acid-base pair. At the same time, OH- from sodium hydroxide would pick up a proton to become water. So that becomes the second conjugate base acid pair. So in other words, HCl and Cl- interconvert by the transfer of a proton, and OH- and H2O interconvert by the transfer of a proton. So if in a neutralization reaction, excuse me, you can identify the pairs of species which do this, you'll have identified the conjugate acid-base pairs. So the hydronium ion is the conjugate acid of water. If we were to take this particular example, you'd be able to work out that the acid-base pair would obviously be HCl and Cl- like we've just talked about. The other pair would obviously be the water and the hydronium ion, like so. So it's interesting to note as well that the hydronium ion itself can dissociate again to form water and a proton. In other words, what we can do is assume that the concentration of H3O+ is going to be equal to the concentration of H+. So in effect, the concentration of H3O+ is going to be equal to the concentration of H+. So the hydronium ion concentration is another way of measuring pH, which is what we're about to look at. So pH values are a measure of proton concentration. I'll explain in a minute or so why we use logarithms, but it's really important to spend a moment just getting familiar with how to do this on the calculator. So you'll notice on the calculator in the photo that you have a log button there. So what you do, if you want to work out the pH, but you're given the concentration of hydrogen ions, what you do is you put in the concentration of hydrogen ions. So let's give an example. So your first step will be to enter minus log. So you press the minus button and then log. So next you enter your H+ value. The way you do this is you have 1.25, 1.25, and the little button just almost off the screen on the photograph, and it says times 10 to the power of x. If you press that button next and then put -5, that will give you this in your calculator. So then you close your bracket like that, because the log function will have opened a bracket for you. So I've taken a photograph of my calculator, and it should show you something like that. So the next thing to do is to put an equals sign, which I'm doing now. As you can now see in the photograph. So what if they give you the pH, but they want you to work out the hydrogen ion concentration? In other words, do it in reverse. So because logarithms are calculated generally to the power, to what we call base 10, to reverse a logarithm you just do 10 to the power of the original number. So if your number was a pH value and it was obtained by getting minus log of the H plus concentration, to get the H plus concentration it's 10 to the power of minus pH. Simple reversal. That should give you 10 with a little square next to it like it's on the screen in the new photograph. The next thing to do is to put the minus sign in and your pH value. So minus, and then your pH value in this case is going to be 3.45. So 3.45. Which should now be appearing on your screen in the photograph. Which gives me that value, which is the calculated value, but rounded to 3 significant figures. So please feel free to pop this into your calculation, you'll see what I mean. So it's well worth going away and having a think about this. And it's also a really good idea to make sure you've practiced this interconversion extensively, so it's almost like you don't have to think about it. Because there are more complex acid-base calculations that you'll need to be able to do at A-level, and they will assume that you'll be able to convert between pH and hydrogen ion concentration easily and confidently. So logarithms basically are a way of dealing with very large scales and making them more mathematically manageable. So if we consider the linear scale, 1 to 100, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on and so forth until you get to 100, that's easy enough to plot on a graph, for example. But what would happen if you had to deal with the scale 1 to 1 million? Well, you could use standard form, sort of 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4. But what if you also had some points that were very close to each other within that linear scale of 1 to 1 million? So logs allow us to deal with such scales commonly found when dealing with H plus or OH minus values. So if you think about a solution of pH 1, it's going to have 10 times the hydrogen ion concentration of a solution of pH 2 and 100 times the H plus concentration of a solution of pH 3. And a solution of pH 1 has 1 times 10 to the power of 14 times the hydrogen ion concentration of a solution of pH 14. So that's 1 with 14 zeros after it. This gives you an idea of the scales we're talking about. So as such, we need to use logarithms to help us manage this. If we were to try and use that kind of scaling in a linear way, it would be impossible. It would be mathematically extremely difficult. So let's have a look at strong acids first of all. So working out the pH of a strong acid is actually quite straightforward. And we rely on the fact that strong acids dissociate completely, so we can assume that the concentration of the acid is equal to the concentration of H+. It's important to remember as well that if we have a dibasic strong acid, the H+ concentration is going to be twice that of the acid itself. So for sulfuric acid, for example, it can be assumed that you've got 2 moles per decimeter cubed of H+, if let's say you had 1 mole per decimeter cubed of H2SO4. As a result of this, the value of H plus is readily available to insert into the pH expression. So all you have to really do is find the concentration of H plus in moles per decimeter to the -3 and then put it into the pH expression, and the job's done. There are two ways to work out the pH of a base. One of these methods uses an idea called the ionic product of water. Now you've already seen that water is at equilibrium, it dissociates. And this is actually, the forward reaction is actually an endothermic process. So hotter water will have the position of equilibrium shifted to the right, which means it'll have a greater hydrogen ion concentration and therefore a lower pH value. But simultaneously it also releases an equal number of moles of OH-, so the extra H pluses are offset by extra OH minuses. So its neutrality is maintained. It's actually the only substance which can do this. So if we write a Kc expression for this equilibrium, you'll end up with something like what's at the bottom of the screen. However, to all intents and purposes, the value of the concentration of water is barely changed. In other words, water remains virtually constant in terms of its concentration. So in essence, you can actually ignore the water and write it as H plus concentration times OH concentration. The reason for this is the actual amount of water that dissociates is very, very, very small. So the concentration of H2O really doesn't change at the beginning and at the end of the forward reaction, so it's ignored. So we can essentially say Kw, which is given the name the ionic product of water, is the concentration of H plus times the concentration of OH minus, which at 25 degrees centigrade carries a value of 1 times 10 to the minus 14. And this allows us to actually work out the pH of bases. So in a sort of roundabout way, I'll come round to talking about the pH of bases in a second. So in the same way that pH can be worked out, you can also work out pOH for a base. And the maths of the ionic product of water equation will lead us to the fact that pH and pOH of the same solution will equal 14. No coincidence, because that's the logarithmic scale we use for the pH values. So method 1 for working out the pH of a base, you work out the pOH using OH-, so using the OH- concentration and the expression I've just provided here. You then do 14 minus pOH, and that gives you the pH of your base. So the second method is to use the ionic product of water. We know that this is 1 times 10 to the minus 14 at 25 degrees centigrade. So assuming that you're not dealing with a different temperature, in which case you would be given the different value for Kw. Assuming you're dealing with 25 degrees centigrade room temperature, your H plus concentration is 1 times 10 to the minus 14 over OH minus. And therefore, once you've got the H plus concentration, you can plug that into the pH expression there. Nice and simple. It's worth pointing out as well that, if possible, try and get used to using the Kw method, because the Kw value is on the data sheet that you'll get in your exam. In other words, you don't have to memorize this 1 times 10 to the minus 14. It's actually on the exam data sheet that you get. So it's a slightly more sophisticated way of doing it is method 2, although method 1 works perfectly well. So if we look at our weak acid, it doesn't fully dissociate because it's an equilibrium, and the position of equilibrium actually sits quite far to the left. So what this means is it's actually quite difficult to try and work out what the concentration of hydrogen ions actually are, because you don't know how many of the HAs have actually dissociated to make hydrogen ions. So we have to use a slightly different method than we used for strong acids, because we can't assume that all of the acid molecules have dissociated. So the Ka value is essentially the same as the Kc expression for this particular equilibrium, and it'll be worked out in exactly the same way, with the products being the numerator and the reactants being the denominator. Now the only slight problem we've got is that in the question we'll only be provided with 2 out of these 4 things. You'd be given the Ka value for that particular weak acid, and you'd be given the original concentration of the acid itself. So that means we actually have 2 unknowns. This is a mathematical difficulty, but there's a way to get around it. In the product side of the equation at the top, the H plus and the A minus are equimolar. In other words, for every 1 mole of weak acid that dissociates, you get 1 mole of H plus and 1 mole of A minus. That means that you can consider the concentrations of H plus and A minus to be identical, which allows us to greatly simplify the Ka expression. So now what we can do is we can rearrange it so that H plus is the subject. And we do this by doing the square root of Ka times the concentration of HA. Remembering, of course, that Ka and HA are both provided in the question. So then we can utilise the standard pH expression and plug the value in that we've just calculated. So what we need to take advantage of here is the fact that Ka and HA are both provided by the question. Without them you wouldn't be able to do this type of calculation, so all exam questions on this particular type of pH calculation will actually provide those 2 values for you. So this is another very important calculation to go away and practice and make sure that you're well able to do it as applied to any one of a number of different examples that will be given to you. So the Ka expression can be essentially seen as a fraction with a numerator and a denominator. So if the denominator gets bigger, then the value of Ka decreases overall. So in real terms, this would mean that the concentration of HA would have to be larger, and therefore the position of equilibrium in the dissociation of the weak acid would sit to the left. This would also have to mean that the concentration of hydrogen ions would be lower, and as such the acid would have to be weaker because there's less of it dissociated. So this means that the larger the Ka value of an acid, the stronger that acid happens to be. And the Ka value is always given as moles per decimeter to the minus 3. And this can be easily proven by doing some cancelling of units, like so, which leaves us with moles per decimeter to the minus 3. So just like the linear scale of H plus concentration looked at earlier when we were looking at pH, Ka values, they can also vary widely in terms of order of magnitude, so 10 to the minus 8 or 10 to the minus 4 or 10 to the minus 6 for example. And we get around this problem as well by using a logarithmic conversion. And mathematics is exactly the same. So pKa is minus log Ka, and to get the Ka value from a pKa value, the reverse, is 10 to the minus pKa. And if you were to take some examples that show the relationship between Ka and acid strength and plug them into pKa calculations, you'd see that the smaller the pKa value, the stronger the acid, and vice versa. This is an interesting reversal of the proportional relationship to bear in mind when you're doing judgments on the strength of an acid based on its pKa value. So pKa values are used extensively to compare the weak acids we tend to find in biological systems. And like we've mentioned already, they're an easy way of dealing with the wide range of Ka values that you find. So you've come across phenol before in terms of your aromatic chemistry. This time they're going to ask you about it in terms of its acidic behaviour. So it asks you to define two simple terms. So they're easy enough to deal with. We've already talked about what a Bronsted-Lowry acid is. It's a proton donor, and we've said that a weak acid partially dissociates or partially ionizes. So now let's have a look a bit further down the page. When phenol is mixed with aqueous sodium hydroxide, an acid-base reaction takes place. And remember what we talked about when we were doing our work on conjugate acid-base pairs. The conjugate acid-base pairs have to be interchangeable by the transfer of a proton. So if we look at phenol, we can say that because it's behaving as an acid, we can call it acid 1. And because what it turns into when it loses a proton is the phenoxide ion, the phenoxide ion can be base 1. And these two are interchangeable via a proton exchange, or a proton transfer rather. So now what we must be thinking is what's base 2. That's obviously going to be the OH minus ion, because we know that behaves as a base. Which means that water must be the acid 2. So OH minus and H2O are interchangeable via the transfer of a proton. So looking at the next part, they've been a little bit sneaky, because they've given you a solution of phenol in water has a concentration of 38 grams per decimeter to the minus 3. They will put this into exam questions every now and then to see if you can convert that into moles per decimeter to the minus 3. So in the same way that moles equals mass over mR, moles per decimeter to the minus 3 equals grams per decimeter to the minus 3 over mR. So what we've got to do is we've actually got to work out the concentration when we're doing the pH, but in moles per decimeter to the minus 3. So I'm going to leave that one there as a reminder. And we need to do the Ka expression. And it should look something like that. Now just to double check, to make sure you're on board and convinced of this, let's have a quick look. And there you go. So phenol will dissociate into C6H5O minus and H plus. So now what we have to do is calculate the pH, and the first thing to do is to get the concentration. So that comes out at 0.40 moles per decimeter to the minus 3. Now we've got some numbers we can plug into our Ka expression to get the pH of our solution. And we know from our previous slide that we can convert the Ka expression into H plus squared over C6H5OH. So the concentration of H plus squared divided by 0.4 is going to be our Ka value, and we're told the Ka value in the question as 1.3 times 10 to the minus 10. So we can plug that value in here. And by rearranging the Ka expression so that H plus concentration is the subject, we get the square root of 1.3 times 10 to the minus 10 times 0.4, which gives us 7.2 times 10 to the minus 6 moles per decimeter to the minus 3. But we're not out of the woods yet, because they want us to do the pH of the solution. That's just the concentration of hydrogen ions. So we need to do pH equals minus log of the 7.2 times 10 to the minus 6. And that gives us a value of 5.14. So just quickly checking our mark scheme, we said that it was a proton donor and that it partially dissociates and ionizes if it's a weak acid. We got the acid-base pair for each. We got the Ka expression, and we correctly converted grams per decimeter to the minus 3 to moles per decimeter to the minus 3 as 0.40. We used H plus squared and inserted all the numbers into the Ka expression, which gave us 7.2 times 10 to the minus 6 as the value for H plus, and from that we could work out that it was 5.14. There's a few common mistakes you can see at the bottom, so always remember the square root, and the non-conversion of 38 grams per decimeter to the minus 3 would have lost a couple of marks there, so it's really important that you make sure that you don't fall into that trap. Watch out for the units of concentration that they give you. So hopefully you found this a fairly useful clip. Thanks for your time. I appreciate you spending the time listening to it. And any queries you've got, please bring them into your teacher, or maybe have a chat to one of us in a subject extension at college. So for now, thank you very much and see you soon.